Okay, so I'm Dreia Carrillo, aka Andromeda, and I'm going to talk about satellites. But first of all, I kind of want to give you guys a disclaimer that I'm going to be using Comic Sans a lot because I saw this Facebook video, and I get everything from Facebook basically, that says that Comic Sans just like gets the audience attention a lot more. So just gonna say I'm sorry for all the Comic Sans that you're gonna see. All right, so I'm gonna talk about satellites, but not the International Space Station kind of satellite, not that, but these small things over here. And how do I use the pointer? Over there. So these two. And Mike kind of talked about them already a while ago, but just to make sure that you guys know them, you could see them in the southern hemisphere, but even if Austin were in the southern hemisphere, you probably wouldn't see them because it's the light pollution just sucks. But can you guys tell me what they are? Also, I have bribes here. I got starbursts. So if you could... All right, perfect. I cannot throw this right now. All right. You got one right there, sir. I suck at that. Anyway, I cannot play football. All right, so those are the Magellanic Clouds. So I'm going to be talking about these kinds of satellites instead. And there's a bunch of these dwarf galaxies, or satellites that go around the Milky Way and Andromeda, and there's tens of them. And even outside of our own local group. So I basically just copy-pasted a bunch of them just to like prove the point that there's a lot of them going around our own galaxy. So I'm going to be talking about dwarf galaxies. Exclamation point and all caps in Comic Sans to make a point. All right. So hopefully by the end of my talk, I can prove to you why these kinds of galaxies are worth the time and effort and a lot of money with our very best telescopes right now. And as Mike was saying a while ago, the one that we have right now are right about like 8 meters to 10 meters. So this is the Subaru Telescope. It's 8.2 meters, and it's in Mauna Kea, Hawaii. This is the Very Large Telescope in Chile, and it's 8.2 meters times 4, so it's very large. It's much larger than the Subaru. And there's everybody's favorite space telescope, which is... All right, I don't know who to give this starburst to, but all right, there you go, sir. You're much nearer. All right, so hopefully by the end of my talk, I can prove to you that all our best resources are going to be very useful, and it's worthwhile to use them to study these dwarf galaxies. Because at the very base of them, dwarf galaxies answer a very fundamental thing about the universe that we see today. Because we believe in this cold dark matter universe, which is basically we have the dark matter, which is it's cold because it moves very slowly and it's very massive. And simulations of cold dark matter universe reproduce the universe that we observe. So, for example, here's a god-awful colored simulation of clusters of galaxies, and they reproduce the same properties that the even better real-life simulation of clusters of galaxies that we have. But when it comes to much smaller halos in those clusters of galaxies, like the Milky Way, we run into a bunch of problems. So one of them is we do not see as many satellites as, oh, shoot, here we go. We don't see all these many satellites in the observations compared to the simulations. And this is called the missing satellites problem. But astronomers can kind of like go around that problem by, just adding more of baryonic physical processes into their simulations, but that's kind of expensive. Another problem is that the satellites that we observe do not have as much dark matter content as what is predicted for them, which is called too big to fail. Props to Mike again. Yeah, so there's that. And then lastly, that I'm going to talk about is that the dwarf galaxies that we observe are actually arranged in a planar distribution, both in the Milky Way and in Andromeda, which is the other big galaxy in our local group. And this isn't really reproduced in the simulations that we have. So, same Jackie Chan, I don't know either. And that is why we kind of want to look more into these dwarf galaxies and just, understand them more and whatnot. The physical processes involved, their distribution, all these other properties in order to give us a better insight of, the universe that we live in. So I'm going to talk about the way that we observe them. So this is, can somebody tell me? It's actually kind of a trick question. Yes? With what? No, it's not. But A for effort, sir. What? Well, true. Okay, this is kind of a trick question because this is actually like an artist's rendition of the Milky Way if we were an alien civilization that's kind of like facing it like that. Yeah. Yeah, but we do not see it like that because we see it as a band because we're in the spiral arm. So there's the Milky Way, and this is, as I mentioned a while ago, hopefully you guys remember. Someone said that. I didn't know. Sir, you already got it a while ago. I'm going to throw it at a different... Okay, there you go. So there's the Large Magellanic Cloud, and this is the... Okay, you guys are making it very hard for me. I'm going to throw it here. And this one, which is kind of pretty hard, whoever answers this deserves 2 starbursts. Very close there, but no. No. I'm going to take it. It's a Sagittarius Dwarf Irregular Galaxy. So the orange starburst is mine. All right, so this is the Milky Way, and I'm just kind of going to give you guys a scale of how the other dwarf galaxies compare to our own main big galaxy. So that's the Milky Way, and that's the Large Magellanic Cloud, and that's the Small Magellanic Cloud, and that's Sagdig. And so this is how we're probably going to see them if they're nearby. But if we want to learn more about these dwarf galaxies, we have to look beyond the Milky Way. We have to look beyond Andromeda. And so we look outside of our local group. But that means they're definitely much farther away, and you can barely see galaxies like this small. So definitely it's much harder to look for greater distances, especially if they have very diffused light. So for these galaxies are actually from M81. So for the top 2, you can kind of see, okay, there's something there. But for the bottom 2, you can't really say that there's any dwarf galaxy over there. So then astronomers have to be very, very creative at trying to look for these things. Anyone got that reference? It's from The Little Prince. It's my favorite thing. But yeah, so kind of backtracking, let's figure out what a galaxy is made of. So we have our frying pan, and we have our stars. We have our, that's actually dust, but true. Yeah, that could be dark matter. That's close. It's from Spirited Away, but I guess not a lot of you guys have watched it. And we have our gas, and then dark matter. Perfect. And then we cook them in this frying pan that is gravity, and then we get our galaxy. So a neat way that astronomers try to look for these dwarf galaxies, or just other galaxies in general, is that if they don't look like a dwarf galaxy, we look for the stuff that make up these things. So I kind of said it a while ago already. The easiest way to look for them is to look for things that actually look like dwarf galaxies. And dwarf galaxies have very diffuse light. So these are some of the candidate dwarf galaxies in M81. Very far galaxy. I kind of don't remember how far away it is. But so in these parts, you can't really tell that there's anything there. But it was taken with the Hubble Space Telescope, so we kind of trust it. So that is the easiest way to look for dwarf galaxies. You can take it, well, this one is taken with a Hubble Space Telescope, but you can definitely do it with your ground-based telescopes as well. You just need better exposure time, and again, it's kind of hard to get time on those very competitive ones. Another way to look for dwarf galaxies is by just actually resolving the stars themselves, and then seeing that, oh, there's a concentration there and whatnot. So this is actually what I did for my undergrad research at University of Michigan. Yay! Go blue. Anyone? Anyone? Nah. All right, so for what I did for my research is that I looked at this specific field in NC 5236 or M83, and this is from the GHOST survey. Galaxy halos, outer disk, substructures, something. It's very long. And we look at the outer parts of the galaxy to look basically at the stellar halo, because the galaxy actually extends much farther than the disk that, is pretty obvious. And this stellar halo is composed of a lot of the stuff that's been accreted from these satellite galaxies, from these dwarf galaxies that I'm saying is very important. So what I did for my research is I looked at this specific field 10, kind of zoomed in here, and I don't know if you guys could see it, but all the green, red, and blue dots right there are actually the resolved stars for this galaxy that's 30 million light years away. And so we figured out that, there's that very anomalous concentration of stars right there. We further looked into it, and so I published a paper. Yay. All right. And then I think one of the cooler ways to actually look for these dwarf galaxies is by looking for gas. And gas is what makes stars. And that's why, kind of just like putting two and two together. We can look for gas and then see if there's actually some associated stars with them. So this M81, and that's, I think is M82. And usually, we look for these fields, this neutral hydrogen fields, and then see if there are any peaks, and then try to see if there are actually stars correlated with these. So I told you how to look for dwarf galaxies. So now what? Should you really care? I say yes. Because then here comes the very fun part. You can do follow-up studies on them and see their chemical compositions or distance to their main galaxy or morphology, like how their shape is and like their color. Because, so what? Because dwarf galaxies not only just tell us about, the history of the universe, like with the stellar archaeology that Mike was talking about, they can also tell us the history of the galaxies that are just like basically near us. They're these nearby galaxies that we see in posters and whatnot, and are very, very beautiful because they contribute a lot to the evolution of these galaxies. So for example, there are these streams that we see around the Milky Way. There's a Sagittarius stream, Orphan stream, that stream over there. And it's probably hard to kind of picture that with just this with this image taken from our galaxy itself. So here is an alien view of the streams of Milky Way. So they go all around our galaxy. And these are satellite galaxies. These are dwarf galaxies that go and get near our main galaxy, and then its stars get stripped. And not only that, it doesn't only happen in the Milky Way, it happens for all the other galaxies that we know, and they make for pretty nice background pictures. And it's not just in the streams. They get diffused in this like massive stellar halo, and by looking at them, we can kind of see how enriched our galaxy is. So aside from building the outskirts of our spiral galaxies or other galaxies, we also need these dwarf galaxies to build a massive bulge and also a disk. Because as they come closer to the main galaxy, there's this drag, this dynamical friction that basically pulls it near the center. So it adds more stars and star formation here. And at the same time, it induces this stellar bar right there that also pushes more gas and stars into the central part that builds the bulge. So dwarf galaxies are responsible for a lot of, for the way that we see the universe today. And kind of just going back to what I was talking about a while ago, about simulations, we need more observations of these dwarf galaxies because we want to update our belief of the universe. We want to put more of the physical processes and properties that are involved so that we can predict more things and ask more questions. So I hope if there's anything that you learned from my talk, this is kind of fast. I hope it's that tiny things like these dwarf galaxies actually have a big impact in the universe that we see today, and that also Comic Sans is okay sometimes. All right, thank you.
Okay, so we have some time for questions for Andromeda. Oh, there's one behind the person that just stood up. Okay.
Yeah, so good question. There's actually they live in a very different area in this I think radius versus absolute magnitude graph. So they occupy very different areas and actually follow very different trends. But there's kind of there's a gray area wherein they kind of overlap, and you don't know where the object actually belongs to, if it's a dwarf galaxy or a globular cluster, and those are the ultra faint dwarfs. Yeah.
Down in front.
I was wondering, on the Milky Way, how far out does our gravitational influence reach?
Okay, the question is, in the Milky Way, how far out does our gravitational influence reach? So a lot of these, the dwarf galaxies that are kind of associated with the Milky Way are right about, I would say, 700 kiloparsec times 3. So 21, yeah, that much. Because Andromeda is right about that far away from us too. So there are ones that are more affected by the Milky Way, and some that are more affected by Andromeda.
Yeah, what's a kiloparsec?
Oh, a kiloparsec is, okay, 1 parsec is equal to 3 light years. Yeah. And a parsec is what we usually use as astronomers. Yeah. Yes.
You were talking about how the dwarf galaxy affects the structure of the main galaxy.
Yeah.
What's the breakdown between how much is the dwarf galaxy and how much is the dark matter for making that structure?
How much is a dwarf galaxy and how much is a dark matter? Okay, so a dwarf galaxy is, it's the dark matter of a dwarf galaxy. It's the stars, it's the gas, it's the dust, and it's all of that. So basically, when the dwarf galaxy collides with its own, with the main galaxy, the stars follow this, this stream because they're tidally disrupted. Before the dark matter, I'm not completely sure, but I think it just gets kind of incorporated. We don't know if it also gets tidally disrupted, but I wouldn't think so. But yeah, but it also gets incorporated into the main galaxy when they collide.
Well, let's thank her again. Thank you, Andromeda.